Hello everyone, thank you for watching our presentation about our project to optimize trout fisheries in California. Today presenting is me and Thomas. This project intended to predict and prescribe the best conditions and locations to raise the largest trout for sustainable fisheries. The data was from natural inland fisheries over a 24-year span within 7 counties in California. With this data and supporting models, recommendations can be made to optimize trout size production and sustainability. We narrowed the scope of this project to only include the rainbow and brown trout to narrow the unique records included in the analysis. California Department of Fish and Wildlife collected the data set with over 20,000 unique records and 25 species of fish within the records. We needed to narrow down the scope of our project. To narrow the scope, we needed to understand the different species included in the original data set. Once we understood the data set, we were able to have a more reasonable number of records relevant to our study. The data was obtained from data.gov, and the metadata was last updated October 2021. Over-harvesting natural fisheries negatively impacts the financial stability through tourism and sports and ecologically. With a lack of information on how to optimize sustainable farms, this proposal uses gathered data to improve the sustainable farming resources of fisheries in California. By identifying the key factors that lead to a large fish length in trout, we can design sustainable inland fisheries that yield a superior product. This project was broken into 2 sections. The first section was a predictive model that used multiple linear regression models about environmental variables to determine the trout length in millimeters, and the variable coefficients were collected from the predictive model. The second portion was a prescriptive model that used linear programming to determine the best location and conditions. The prescriptive model process included 2 sensitivity analyses to measure the validation of the location under different scenarios. The data exploration was an opportunity to examine the variables and identify possible issues with variables. The continuous variables basic statistics are shown in the table in the right corner. There are 6 variables with the response variable as the fish length. We also included 6 locations. We retained the outliers because our objective is to increase the fish length, making a larger number valuable. We transformed the variables to address skewness and kurtosis. Our figures show Parsons correlation, which generally looks acceptable. The water pH level appears to have a higher correlation with water temperature, conductivity, and hardness, which makes sense since temperature and material would impact the pH level of the water. If the bodies of water is smaller, it is reasonable that there's some correlation. All the predictive variables have a good correlation with the response variable. No transformations were necessary based on the data.
Our predictive model used a multiple linear regression approach. Our model used 4 of the original 5 environmental predictors in order to explain the change in fork length. Temp, hardness, conductivity, and flow were chosen to be used in the model, utilizing backwards elimination, where each instance was based on the most significant decrease in a Kayaka value. After the initial model was made, the VIF was taken for all remaining variables, and none had a VIF higher than 1.5. Also, all variables were below a correlation of 0.8 to each other, so the possibility of multicollinearity was not present. To build our model, we utilized 10 k-fold cross-validation in order to train our model on multiple different training sets. It was found that out of all 10, model 9 in the iteration was the best performing based on the lowest RMSE. It did have the highest MAP, but the difference between MAPs of each set was significantly less than the RMSEs of each set. The model itself was only able to predict 12% of the variance of the test as seen in its 0.1208 test R squared, but it did score an MASC lower than the naive model. In the middle figure, we have a graph of the model's predictions versus the actual lengths of the fish for those observations. In our prescriptive analysis, we use the location's natural maximum and minimals for our environmental variables. Our model required that one and only one location be selected to use, and that the amounts of temp, hardness, conductivity, and flow must be chosen within the natural constraints of the location itself. When optimizing to maximize fork length, the model found L Portal to be the best location and to use a temp of 21 degrees Celsius, a hardness of 14 parts per million, a conductivity of 30 microohms per centimeter, and a flow of 45 cubic meters per second. Once optimized, we performed two sensitivity analyses. The first one can be seen in the figure in the bottom right, and it shows the results on location selection if we extended the maximum temperature constraint in the sands location to 25 degrees Celsius. The model, even under these conditions, still favored the L Portal location. The figure in the middle bottom shows the results of the secondary sensitivity analysis, where we not only allowed for the increase of temperature in the sands location, but also for the artificial increase in flow in that location. Even with those two factors both being increased, the model still chose to use the L Portal location with those conditions. In order to build a successful prescriptive model, we took the results from our predictive model and used it as the objective function for our prescriptive model. Here you can see the multiple linear regression model that was used for the predictive model and how it was translated into our prescriptive model's objective function. We can see that both temp and flow were positive contributors to fork length, where hardness and conductivity were negative contributors. This would explain why the model would want to focus on locations with high temp and flow, but low hardness and conductivity. With our model's chosen location, which was the L Portal location, and the chosen parameters, we see that our expected fork length should be 183.3 millimeters, or roughly 7 inches. In conclusion, based on our modeling, the L Portal location should be chosen for our next sustainable trout fishery location. We should also keep the water at 21 degrees Celsius, keep the hardness at 14 parts per million, keep the conductivity at 30 microohms per centimeter, and keep the flow at 45 cubic meters per second. These conditions, though, do only account for 12% of the variation in fork length. Things that should also be considered are that these environmental factors alone are not sufficient for producing fish of a large fork length. When we are setting up our fisheries, we should be looking for good stock to be as our first introduction. We should be looking for fish with a pedigree of producing large offspring, and those should be considered over fish that produce a small offspring. Selective breeding techniques should also be practiced, as those will also help give us more consistent fork lengths from generation to generation.